Okay, I hope you can see my slides. So good evening, everyone. My name is Ariel Moskovich, and today I'm going to talk about Kafka rebalance. I'm going to dive into different aspects of rebalancing a production cluster that is under high throughputs and have a lot of data. So I hope it will be interesting for all of you. So thank you for joining. So in today's agenda, I'm going to give you some context, talking about Kafka at Wix, a quick refresher for Kafka terms that I'm going to use during this talk. A little bit about the problem. What is the problem that I'm trying to solve here? What was the motivation to solve this problem? When we are talking about Kafka rebalance, what are we actually balancing? What are the different balance verticals that's included in that process? What are the stages of for this balance? How the results look like? And how we are going to test those results. So that's me. At the last year, I'm working as a system architect at Wix. My 4 last roles, I'm working on a high-scale web companies, and in my 2 last roles, I'm doing Kafka intensively. So I guess we are all share the same enthusiasm about Kafka. And this is my first meetup in pajama, doing it in pajama. So that's a new one for me as well. I don't know if it's upgrade or downgrade, but it is what it is. So at Wix, we have several types of clusters. So first, we have our production cluster, which we are producing and consuming to them locally in each of our regions. Those clusters are running on the right throughputs and have a lot of topics, around 15K, tens of terabytes of storage. If we will include the other flavors, we probably will get into hundreds of terabytes. And we also enabling to replicate the data between region by a tooling that was created by our server guild. But basically, we are producing and consuming to those clusters locally. And we're also using Kafka for stream with Debezium to ingest our websites events into our BI system, and also as a middleware for our logs. So before we start, if you are planning and you are find this process valuable for you, and you are using Confluent Enterprise platform, I want you to know so you already have tooling that is ready for you. If you're using older version, there is the Confluent Rebalancer tool. And if you are using newer version, they have some kind of a self-balancing cluster. And the concepts that they are using for those tools is very similar to what's the concept that I used in my process. But it's a process and it's also very interesting to know what happened behind the hood. But basically, if you do need it and you are using the enterprise version, you have those tools ready for you as a note. Okay, so quick refresher. So Kafka cluster stores the events, the messages into categories called topics. If you do it right, you are placing different messages, different message types into different topics. The cluster itself consists obviously from servers. Those servers are called brokers. Each topic maintain a partition log, and the concurrency of a topic defined by the number of partitions for that topic. So also, each one of the partition is being populated by one broker or more. So if, for example, we're running in a topic with a replication factor of 1, this partition will be populated by one partition. If we look in the example below, sorry, at the right, we can see an example for a topic. So partition 0 in that case is being populated by broker IDs 0, 3, and 2. Partition 1 by broker 2, 1, and 4, and so on. So it's and each one of those partitions is a file as a node. So if a topic is if a broker is participating in more partition, obviously in the cluster there will be more utilizations that this, or more work that this broker will needs to do, because it participating in more partition, is holding more files, more data is being produced to it, more data is being replicated to it, and so on. So it's important to keep that in balance. We will talk about this in a second. Also, those broker replica regarding two terms called ISR, in-sync replica, which means that one of those broker act as leader. The producing of the client is done to that leader, and the leader is replicating the data to the other broker in this ISR. So it's extra loads on that leader. So it's also an important to balance the leadership of brokers inside the clusters. Okay, so so what is the problem statement? What are we trying to solve here? So when we have a cluster that is in production and is have a high throughputs, and we want to increase it and to add more capacity to it, by definition, if we will add more load to it, that's we want to minimize the extra load that we will involve in that process in order to not push it down the cliff. So we want to be able to expand the capacity to this cluster with a minimum interference to the producers and consumers. If we will do it too aggressively, the producer might experience errors. We will have error to produce to this cluster, and the consumer might get into lags in the consume. So we want to avoid that. And when you are approaching this problem, we can do it in a simplistic way when we are taking a structure of a topic that is being divided into partition and into broker, and then when we're adding extra capacity to that cluster, when I'm saying extra capacity, I mean we are adding new brokers to that cluster without assigning any partition to it, without assigning it those brokers to be leader. Those brokers are not going to do any work. So if we will take one topic and we will just reshuffle the new brokers and we'll create a new structure of this topic with the new brokers, eventually what will happen that this topic will statistically distribute or balance the partition count and leadership better than before on that topic. The problem with that will also cause a lot of data movement in the cluster, because then we need to move pretty much start moving from data from any broker to any broker. And that can cause, of course, very high CPU utilization, network saturation, and errors to producing and lags in consuming. So we want to avoid that. What we do want to do is to minimize this data movement as possible. And how we can do that is by calculating the minimum changes that we need to do in each of our topics in the cluster in order to achieve the same goal or the same balance. So what are the different things that we want to balance in the cluster? So first, as I said before, we want to make sure that the partition per broker, the partition count per broker will be balanced. If we have, for example, cluster with 10,000 of partitions and each broker is holding, let's say, 1,000 of partition, this is pretty much a balanced state. But we have brokers that's holding 200 partition and other that holding 800 partition and so on. This will create a scenario when some brokers will do more work than the others, will hold more data than the others, we will produce to them more, we will consume more from them, we will replicate more data to them. So this will cause an unbalanced cluster. So we want to make sure that the partition count per broker will be very close between the brokers. Another factor is the leadership. Like I said, brokers or clients are producing to the leaders in each one of the partitions. If there is unbalanced states and there are brokers that have significantly higher leadership count than others, what will happen that they will be more, they will be saturated because you will also produce or the produce load will be minimized to just few brokers, and also because they are responsible of replicating this data to the replicas, and this data need to be copied from them to the replicas, then that they can get into a situation of network saturation, because they will also have more network from the clients and more between them and the replicas, which will cause them to be saturated. And this can cause a cascadic failure in the cluster because you will have brokers that are being saturated, and then other brokers won't be able to communicate with them and so on. So that's something that is important to balance. And another thing that is a little bit tricky, maybe trickier than the others, is disk capacity. And the reason that is tricky, it's because not all topics are born equal. There are topics that have higher attention than others. There are topics that have higher throughput. And you can have a perfect balanced cluster regarding to number of partition and leadership, but still have brokers with 80% of disk capacity and others with 20%. So in order to avoid those kind of situation, what you need to make sure that specific brokers or specific broker won't have too many appearances in one topic. So we want to spread it to have good diversity of brokers inside each one of the topics. And another thing that can cause that, let's say, if, for example, but this is more like from the creation topic aspect, is if you will create a topic with small number of partitions. So for example, if you will create a topic with one partition and replication factor of 2, what will happen is this, all the data will be written to only 2 brokers. Now, if you are setting this topic with a very high retention, this data will be written to only those 2 brokers and will be accumulated there. So that's something that it's important to validate when you are creating the topics. So what are the rebalance steps? What are the steps that I use in that process? Now, before I will speak about those steps, I want to give a quick description of how the Kafka rebalance being performed. So basically, Kafka has a tool called Kafka Reassign Partition, and this tool is using a JSON file to describe the topic or topic structure that we want to balance. In my process, I created a JSON file per topic. And this is a very simple JSON file. What you describe inside it is give you a list of hashes for the partitions, which will include the data, what is the topic name, what is the partition number, and what are the replicas, which brokers are populating each one of the partitions. Now, for example, in the example that we have in these slides, partition number 4 for topic hello Hemby topic is being populated by replicas 17, 19, and 45. Partition number 5 by brokers 45, 18, and 0. If I will take this JSON file, and let's say that this JSON file is represent the truly status of that topic in the cluster, and will change for partition 4, for example, broker 17 with broker 10. What will happen? That and we'll use the reassign tool to execute this reassignment JSON file. What will happen? The data will start copying from broker number ID 17 to broker number 10, and when this process will finish and the new broker will be completely async, the new replica of partition number 4 will be 10, 19, 45. Of course, I can do this to multiple partition and create more or to create this process for multiple partitions in concurrency. There is another parameter for throttling that can be used for that in order to do this in a throttle way and not creating and control the amount of data that will move between the brokers. So the steps include the first step in that process will be to create the original JSON file. And those original JSON files are the files that describe the status of the topics or the structure of the topics as they are before the rebalance. We then taking those original files and extracting some data from them that will help us to calculate and to calculate what are the minimum movements that I need to do for each topic in order to get into the balance state. And then I will in that process also will create the migration file. The migration file are JSON file for each topic that will represent the desired state for each topic, okay? And after I will have those two sets of files, I will run the test to validate this process. And if everything is passed, I will use those files in order to do the rebalance. This is the configuration of this process. This configuration representing the first base directory where I will create both the original files and the migration files. Also the paths that I need to use in order to get this information from Zookeeper. State file and another parameters are unbalanced ratio, which I'm using, and we'll see it in a couple of slides, to calculate which brokers are underbalanced regarding to partitions, and maximum diff that I'm using for our testing. So in order to collect the data, I'm connecting into Zookeeper. And in that process, I will get all the topics, all the brokers for that cluster, create the directories, create the state file. That's the state file including the topic list and the broker list. And then I will go run over the topics and we'll create the original file for each one of the topics. Now I'm going to check that if that file already exists or not. And the reason is because if this process will break in the middle because some network error or disconnection from Zookeeper or whatever reason, I can continue from the same point and don't have to start all over again. After creating those files, what I'm doing is I'm collecting some data that I will use later in the rebalance process. How many partitions I have per broker, per broker and per topic, and the replication factor. And after I have all this data that I need per topic, I will calculate what are the partition or what's the number of changes that I need to do per topic in order to get into the balance state. So how do I calculate that? What do I do? So first I'm calculating the broker fraction of the new brokers. So I'm taking the brokers that I detected, and I will show how I detect that or how I define that more accurately in the next slide. But I will take those brokers, the new brokers, the one with low or none partition assigned to them, and divide that with the total number of brokers. Then I will calculate the number of broker appearance in that cluster. I will take the partition count for that topic and will multiply it with the replication factor. And then I will multiply the broker fraction with that number. So for example, let's say that I have a topic with 30 partitions, and I have this cluster include 10 brokers, that one of them is new. So what I will have from the broker fraction is 1 divided by 10. This will give me 0.1. And in the number of broker appearance for that topic will be 30 multiplied by 3, that will be 90. And the number of changes or number of partitions that I will need to change for that topic will be 90 multiplied by 0.1. So total of 9 changes. Now, important to say that this will be, I'm making only 1 change per partition. So from the potentially of doing reshuffle of having 90 changes, if I'm just scrambling everything around, I'm only doing tenth of those changes, meaning much or significantly less data movements in this rebalance process. So I'll define the unbalanced broker. Basically, I'm calculating the median for the partition count for the brokers. Then I'm checking if the broker that specific, I'm running over the broker and I check for each broker if the partition count is less than the median divided by the unbalanced ratio. In that case, the default 2. And if it does, it will considered as broker that we can add more partition into it. It will be under-replicated broker. And in the replacement method itself, what I'm doing is first remove the broker with the highest count. And those brokers, both the one with the highest count and the one with the lower count, are being, obviously, I'm sorting that list continuously in this process in order to update it. Also, I'm reshuffling or rotating that list in order to create balance between both the brokers that I'm removing load from and the brokers that I'm adding load to them. So I will first remove the broker with the highest count. I will add the broker with the lowest count in two different manners. One of them, if this broker, and this is something that is important to understand. So in a replica that representing a partition, the broker that reside in index 0 is the one that will be considered by default as the leader of this ISR. So if I found that this broker is leadership count is higher or lower than the one that currently resides in that position, according to that, I'll either insert it to that position or just add it to the replica list. And then I will just update the counters, we'll remove the one from the highest broker, we'll increase one for the lowest broker, and we'll update the replicas counter. So how the results will look like. So basically, at the end of this process, what I will get two directories and two state files. The state file are the brokers and the topics, the one that I've mentioned before, and the migrated and original directories will include all the JSON file that's in the original. We will have all the topics before or as the cluster is the state of the cluster before the rebalance, and the migrated is the desired set. I am expecting to have obviously the same number of files because this process is running over all of the topics. And if we will focus or zoom in into a specific section of specific file, we can see here diff between two partitions of workflow events topic, and we can see that in partition number 3, we replaced broker 24, ID 24 with broker 35. In partition 28, we replaced 7 with 27. So basically, if I will apply that JSON, it will start doing the data movement, we start rebalancing or move the data from broker with higher partition counts to one with lower partition count. So we have the files, then basically what we need to do is run over them, and this process could take a long time. It's defined, it's depends on how your cluster is busy and how you can space this process. Obviously, we do it sequential between topics. We don't. You can have one rebalance process at a time, and we try to, like I said, doing it with the total parameter and do it over time, so we won't overload the cluster. So this is the process of us adding new brokers, and this graph represents the partition count. So we can see that there are new brokers that being added to the cluster, and they are starting to, while we're running this process, get more partitions that they are participating. And the veterans brokers are being reduced. So we are removing load from those and heading to the new ones. This is another graph for the leadership count. And what we can see here is dual operation, actually. Before even heading the broker, we have unbalanced state before according to leadership. So what we did is both adding more brokers and also rebalance the leadership count to the veterans broker as well. So we ended up with much more balanced states from the veterans and for the new brokers regarding to leadership. Okay, so after having those files, we also want to run some tests upon them. So the first one is to test that we are not exceeding the maximum change that we defined as allowed per topic. We're changing that the topics are actually balanced, comparing just checking the partition count, testing that the leadership is balanced, checking that there are brokers, that there are no root brokers that are not included in the state file, checking that the topic click is not, and some generic checks that unit test will be just running. And this is a screenshot of one of the outputs of the check. So we're checking the deviation from the medians for each brokers regarding to partition count. And we can see they are pretty close to the median. The deviation is relatively very low. And obviously, if it's swarmed, it will fail, and then we need to check why and not apply those JSON into the cluster. I want to thank you for listening, and now it's time for questions. So let's see what we have. Okay, I will start with what we have in the chat. Okay. This can be happen. Okay. What the partition is? What if a partition has much more throughputs than others? Do we still want broker to have balance counts of partitions? I'm not sure I understand that, but if you are referring to topics have more throughput than the others, as like I said, we do want to have a good enough diversity of brokers in each one of the topics. Otherwise, we could get into disk capacity issues that I described before. And yes, topics can have obviously higher throughput. There are different categories of different events. So we have specific services that are producing more, consuming more. This is something that is natural and will happen in any real production use cases. And we just need to make sure that those topics are being balanced and have enough partition counts in general, and those partitions are being spread by enough brokers, and obviously also the leaders. Another question, when we are setting replication of 2, then each partition will be replicated to 2 brokers. So replication factor of 2 is each partition is replicated to 2 brokers, that's true, and 3 to 3 brokers, and so on. If you looked at cruise control by LinkedIn, Yeah, I looked at that, and I also had some conversation with Confluent guys. They obviously recommended on their tooling, and like I said, if you are using their enterprise version, it's recommended obviously to use a Confluent flavor of it. But in general, the process or what happens behind the hood for my discussion with Confluent is very similar. Any way to make the process of reassignment faster if you have partition with thousands of data, that will be terabytes. When you decide when to new partition or when you add a new topic. Okay, so we are running this process sequentially, topic after topic. And so the partition in that topic are happening concurrent, not like each partition sequentially, but the topics will be sequentially. And that depends on the loads on the cluster. One way, if we really want to speed it up, because we are running in a distributed data center, what we can do is shift traffic out of the data center, and then we can be more aggressive regarding to the throttling and be faster with this process. But if you have one active region and you have a busy cluster, that's something that you need to consider, understand exactly, and make sure that you won't pass the breakpoint of the cluster, and what can cause, obviously, problems to produce and consume. Let's see if there are two other questions in the Q&A. Anyway, make the process with. Okay, this is the same questions. When you decide when to a new partition, or when you. Okay, I guess this is the same. So you have some SLA monitoring when you do the rebalance live. Do I understand what? Yes. So basically, we are looking on different parameters when we are doing the rebalance. Of course, we can see the throughput on the cluster, see that we are not doing it in peak hours. Also, we are looking on, we have a great metrics from our clients that representing errors to produce or errors from clients, and we will be able to detect if our process is getting into trouble or our clients getting into trouble to produce and consume. But even before that, if the process is too heavy on specific brokers, you will notice this from the cluster metrics regarding to ISR missing. So you will see that there are brokers that are not able to catch up with the leader. And you can. So basically, you will be able to detect this from the metrics, and we have those metrics in order to know that we are not doing any damage during this process. Okay, I think, let's see if we have, no, we don't have any more questions. So at that point, I want to really thank you, and I want to introduce Barak Luzon from Taboola Engineering that's going to give us our next interesting talk. Please, Barak.
Hi, everyone. Thank you for joining. Thank you, Ariel, for the wonderful lecture. It was really interesting. We all love Kafka, so this is really cool. And I hope everybody's staying safe during COVID times. These are not simple times. So, all right. So today we are going to talk about speeding up production with Kafka and Mysql binlog integration. Basically, this is a good example, in my opinion, of a use case that we are using Kafka in a method that is not very orthodox, but it serves a really great purpose on our environment. So a little bit about Taboola. If you don't know Taboola, we are a content discovery platform where we we connect between publisher websites such as HuffPost or the Israeli Ynet or NBC News and advertisers that want to promote their content. And what we will do is try to find a personalized recommendation for the person who's reading their article, who's navigating that website, and try to find a very personalized items that he most likely will click on and will be interested in. A little bit about myself. So I am a scale and big data engineer at the production engineering group within infrastructure engineering at Taboola. I brew my own beer if anybody is interested. Well, not during COVID times, but anywhere else, we can meet up for the beer. So just to start things, and so you can get a clear picture, I want to talk about a little bit about the Taboola data pipe and how it looks. So on one hand, we have clients which might come from REST APIs or mobile phones or browsers for people who are reading an article. And that request to get that recommendations on that same page will get to our front-end data centers. We have 7 of those, 7 front-end data centers that are spread across 7 regions in the world, each with hundreds of front-end recommender services. That front-end recommender will actually try to personalize that through a deep learning model that is deployed to that data center on a daily basis. And then everything that's happened over there will be reported back to the backend layer that we have, which is a data center that is in Israel. That is done via Kafka. The backend processing layer, which has all the buzzwords, Spark, Kubernetes, Hadoop, Vertica, Cassandra, whatever, is actually making decisions about how the deep learning model should look. And we train the model and then we feed it back to the front-end data centers. And it decides on a list of thousands of features that actually close the loop. So you get that reporting back, and then we try to optimize our algorithms in trying to get better recommendations, and that gets written to MySQL DB, the master DB that we have. And it generates also reports to Backstage, which is our partner management system, where our advertisers and publishers can manage their account at Taboola and create campaigns. And those campaigns that are creating are also written to the master DB. And the front-end recommender needs to access that information, and that is done via MySQL replication. So we have one master DB and I'd say dozens of front-end DBs that are spread across the world that enjoy MySQL replication and serve you a copy of that data locally to that front-end recommenders. A little bit about the scale that's going on through what's in it. So we process about 3 billion page views a day. That translates to 500,000 HTTP requests per second to all of our data centers. Our reach is about 1.4 billion unique users a month. And all that translates into 90 terabytes of information, of data that we process on that main Kafka a day. I think that's a little bit higher. Maybe we've passed the 100 terabytes. It's been a few months since I edited that slide. And that 90 terabyte is sent mainly by protobuf messages. If you don't know that protocol, it's a protocol for having a schema, maintaining the schema of messages. We do about 100 billion messages a day on our Kafka. A little bit about the recommendation lifecycle. that is going on. So everything starts at Backstage. The advertiser would want to create a campaign and add a budget to it, add some restrictions to it. I want you to serve it only on specific hours. Do not spend all the money at once. Try to pace the amount of money that is spent. The advertiser will add items and so on and so on. And they'll go on to MySQL DB. And then we have the front-end recommender reading that copy that is replicated to it. And it's reading all those campaigns and restrictions and configurations and recommended items. And we're talking about dozens of tables. And that's a lot of information. Our master DB holds tens of terabytes of data. And through that, the backend processing, as I said before, is doing optimizations for a lot of features, and is also stopping and restricting campaigns from overspending the budget. And that's very important because we have an agreement with the advertiser of not spending more the money than he wanted us to spend. So if we serve a campaign, an item, a campaign that gets clicked after the budget is depleted, we cannot bill the client, and we lost that money. Or maybe we could have earned it in another campaign that is active. So that's important to understand, that fresh data is important to us. So that leads me to the 3 guidelines that we have at Taboola for having a better production. And the first one would be fast response time. And why is that? Well, Taboola is embedded within the publisher's websites. So whatever is going on the website, we have a call from the front-end side of that website in most cases. In some cases are doing via REST APIs to our servers. So the faster that we respond, the better the user experience will be. Also, it will lead to a lower bounce rate, because if you are scrolling through a feed of recommendations and that feed gets stuck, you'll just move on to the next website. And the third thing is it generates a better SEO rating for our publishers. Google just announced a few months ago that it will downgrade websites that have a higher load time, a higher page load event time that is thrown by the front end. So the faster that we are, the better will be for our publishers. And all that translates into a few experiments that we are doing all the time that shows that the lower the response time we have, the better, the more yield that we are creating, the more money that we are creating for the publishers and for Taboola. So we love very short response time, and we have very strict SLA that we have to withstand. And how do you do a speed up of production? As I said, we have thousands of features running on the front-end recommender that need to access a few dozen tables, and that has a lot of information. So the traditional way and the very easy way to do it is via caching. So what you want to do is we will have the master DB layer, and on top of that, we will have local front-end DBs holding a copy of that data. But that's not fast enough, because MySQL actually is in the range of queries on the millisecond. If you are doing very accurate queries, queries by index, you'll still be in the milliseconds range. And if I need to access thousands of queries on MySQL on a single request, that will translate to a few seconds. And a few seconds is way not good enough. Our SLA is much more strict than that. So usually what is done is you can add a centralized cache layer, such as memcached that we have. And memcached is actually a lot faster. It is a key value store that serves you if you want to get the values really fast. It doesn't do all the complicated queries that you do on MySQL, but you can save that complicated query result on MySQL and get a very fast result of what you want. But that's still not fast enough, because you still need to go out on a network, right? Even if it is centralized and it is very fast, we're talking about tens of microseconds to fetch a row from memcached. You still have the network penalty, and you still have the serialization penalty that you have to do on that data that you're keeping there. So on top of that, we added 2 types of caching. That's within the JVM, that's within that's in memory in the service. One of them is a bulk cache where you load an entire table. And that's usually done for relatively small tables that you need to use a lot. And the other one is the major one that we are using and is causing the major load on the system is a by key cache, where you go and fetch from the database or from Memcached whatever you want by a specific key. And then you keep it. And then on the background, you update it once in a while. Okay. So this is really cool. But we have another constraint. We have another guideline for having a better production system. And that is, the more fresh data we have, the higher the yield we have. And that's really easy to explain again, because it makes you get better decisions in real time. So as I said, we have a closed loop of trying to optimize all the features that we are doing and all the personalizations that we are doing. And that this data is kept on MySQL and is calculated on the backend. So the faster I can move that data to the front-end recommender, the better decision-making that I can do and get a better result. And the second thing is that I can avoid serving campaigns that depleted their budget. Now, because we are global, a campaign can be served across multiple regions. Now, I need a shared place that can calculate the amount of money that this campaign has spent in order to understand if it depleted their budget. So this has to be done on the backend, and I need to get this decision as fast as possible to the front ends, because anytime that I serve this campaign and the budget has depleted, I'm losing money. And the third thing is very important as well, is real-time configurations, because if somebody opened a feature flag and that feature flag is actually hurting my production system, then I want to be able to close it as fast as possible. So if I have a configuration that updates once a minute, well, a minute can be a lot of money if you're serving 500,000 HTTP requests per second, okay? So that kind of feels like a little bit of tug of war, right? Because on one side, I want to serve the most fresh information as possible. But on the other side, I want to be able to do it very fast. So I have to cache the data. And to add to all that, constraints, I have the third guideline, which means the lower the load we have on the system, the lower the cost we have. So I want to maximize the ratio between how much money I'm making and how much money I'm spending. Obviously, this is how the company works. So why do I need to reduce the load? It's relatively straightforward. If I need less CPU to do my calculations, then I will need less front-end machines to be able to withstand the same load. And if I will do less queries to the database, I will need less DB machines, right? And that lowers my operation and scaling cost. And in case I have bursts of traffic and I'm not on a constant pace all the time, I can support that burst of traffic and not lose requests. And it's even more interesting than that, because if I free up CPU on a single service, I can actually utilize that CPU to get better personalization. So we have very smart features that understand how much CPU that a specific request is actually using and utilizes it differently. We will do less personalization if we know that the beginning of that request was actually more CPU wasteful. So caches are right in the middle of it, right? Because they're just standing there and they're actually in that trade-off. So the data is only as fresh as the cache TTL, which in our best case is roughly a little bit under 2 minutes, but on our worst case could be an hour. And the trade-off is between having a short TTL, meaning updating the data from the database constantly, but creating a higher load on the service itself by doing a lot of unnecessary serializations of items because the items did not change, or some of them changed, but most of them did not, and creating another load on the front-end databases, versus a long TTL, but serving stale data and having overspending campaigns and getting decisions that are not the optimal decisions. And just to show you a snapshot of what are cache read patterns. So this is our by key cache reads per second. This is for all the caches, but you can see that we are fetching on peak times a little bit over 1 million items per second. That's on a single machine on a single service, right? This is a tremendous amounts of reads. And look at what the caches are helping us to do is reduce that ridiculous number into a very manageable yet high number of doing only 14,000 updates per second. So I've reduced it by 2 orders of magnitude, but if I can reduce that number of 13K even lower, I can save a lot of computing power and utilize it for other stuff or scale up our production without buying new machines. So how do you do it? Like it sounds like an impossible issue because on one side you have caching systems that by design, this is their flaw. But on the other hand, you really want to solve it. This could be a game changer and you can earn more money and have a better production system for that. So I can divide the optimal solution into 3. So the first part would be I want to be able to detect the changes on MySQL tables in some magical way. I need to distribute the changes globally, having these changes as a local copy on each of the data centers. And the last part, and this is the tricky part, would be to inject all the changes to the relevant caches. So I want to be able to skip that whole loop of trying to go to the database and fetch that information and serialize it. I want to react only to changes and not doing that over and over and over again of fetching the same data. So I see we have a question. Maybe I'll try to take that one. How many Memcache machines are you running? Actually, that's changing between data centers, but they're monster machines. They have hundreds of gigabytes of RAM each machine. So it changes because different data centers has different traffic volumes. So I mean, we have I think 3 or 4 on one data center, and the other one could be less or more. That's roughly the average. But again, these machines are huge. All right, so going back to how do you detect changes on MySQL and what are the challenges? So one challenge that we have is that we have multiple sources that change the data. So we have our backstage, batch processing layer, or multiple batch processing layers. We have our backend services, and not all of them are written on the same language. Most of them will be written in Java, but some of them will be written in Python, in Go. We do not limit the language that people are using unless they are doing the same code that's written elsewhere. Most of the code will be in Java because this is our infrastructure, and that's relatively easy to integrate. But then again, we're not always going through an ORM that I can just add like a plugin in it and say, okay, I've detected the change, and then I can do some sort of event sourcing and write that event to somewhere else and say that this piece of data has changed. Some changes are doing via update where query, and that is much faster than working with an ORM. So it's not really possible to have this single layer that is written in code. And the second thing is that it needs to handle an overall large amount of changes. This is a snapshot of the amount of changes, the amount of DMLs that are going on our master DB. And you can see that there are peaks of over 1 million insert, deletes, and updates a minute. So our master DB is busy, and there are a lot of changes, and anything that is written needs to be very fast and very lightweight. So luckily, we've read a thing and two about MySQL replication. And I want to explain in a few words how does MySQL replicates from its master DB to the slaves. It uses a thing called a bin log. It's a binary log of every change that happened, every transaction that happened on the master DB. And you can configure it to include, as well as the query itself, you can configure it to include the rows before and the rows after the change in that same transaction. And what will happen is that the slave nodes will actually connect to that binary log. It's a streamed process. It's not actually reading the files on the disk, and it will get these changes, and it will replay them on its relay log on the slave, and then it will have all the transaction and all the data changes. Now, every transaction is assigned with a global transaction ID. This is as of, I think, MySQL 5.7 or something. So you can actually identify all the transactions, and you can make sure that you're not missing any transactions from the master. And there is one constraint in that, that the relay log on the slave will have to be running in a serial manner. And the reason for that is because if you don't do it and you are performing update operations, you will have data integrity issues on the slave. So it is serial, and that's very annoying. And we found a library from a person called Shaiko. That's the username on GitHub. And this is a library that actually allows us to connect with a Java client and get all the changes from the binary log already serialized in a very convenient way. So that's what we did. We've wrote our own binlog service. And the cool thing about it is that I'm not bound to that serial processing limit, because what I do is I say that if you want to use that fast track, that change tracking with the binlog, you need to have a timestamp on that record that you are changing. And that timestamp has to be, well, the time of the change. And that's easy because, well, most of our system was already built this way. We didn't have to add that constraint to new tables. And we already had that because we were tracking changes in case we needed to revert some of the changes back and know what was going on. I can filter it easily. I don't want all the data. I don't want all the terabytes that's going on through MasterDB. All I want is the critical path and the ones that will make the best impact on my production environment. And so I have also a better control on that service, because I can decide to separate that data streams and say that one service will get a bunch of these records and the other service will get different records. And we've achieved 0 data loss with it, at least once delivery. So it means I can deliver some of the data points twice. And that's with the global transaction ID tracking. So it means that if I haven't processed that row, haven't fully processed that row and send it to the data pipe that we'll see in the next slide, then I will not commit that GTID. And if I need to restart that service, I haven't lost the thing, and I will just go ahead and read that GTID over again. And the cool thing that I get along with it is better visibility, because as you can see here, I can actually see what's going on through the data pipe and on a table level. And if any of you worked with MySQL and you had replication delays, you don't know what's stuck. You just know that you are in a delay behind the master DB, but you don't know what you've missed. But here, I can see what I tried to send, and on the other side, I can add the same metrics and see what I've read. So I can actually do that cross between them and understand what pieces of information have I missed, or am I still waiting for. So we're done with the first part. That's really cool. I see we have a few questions. So there's a question about how big are the on-machine matches, the by key caches. So the machines that are our front-end recommenders are quite large. They have about 40 cores and between 100 and 180 gigabytes of RAM. So they are large, and the caches are a very large part of that. So we want to be able to serve any information without going outside the process even once. We have to do it for the deep learning model and real-time bidding, but other than these two, we are not going outside the process for anything because we want to be able to do it fast. Is this MySQL replication tool publicly available? So you can use that same library that we are using. It's very, very easy to integrate. And if you want to try to do it, and if you have any questions, you can contact me directly, and I'll be happy to assist you in starting this. But our tool is dedicated to our needs, so I don't see the advantage of using our tool. And what's the quorum level you've used? Quorum level on what? I'm failing to understand. So if you can clarify that question about the quorum level, where? Okay. Do you need to strict order guarantees, strong consistencies? It's just a bonus. So yes. So what's going on is that, as I said, every record that's changed has the update time on it, and so the receiving service of that change can decide what to do with it. So all of our caches are trying to do some sort of comparison of timestamp and trying to understand whether a row has been deleted before and I need to ignore it now, or I have received a new row and it's comparing the timestamps. So I do need to keep consistencies, but I can do it in parallel. I don't have to keep these in the events received in order, and it's even a little bit impossible, and we'll see why. So the second stage would be to distribute the data globally. So we've already seen that we can use Kafka for the distribution. Kafka is an amazing tool. The cool thing about it is that I can have one service writing it to a topic or two or three or how many topics that I want, and have an infinite amount of other services that are reading it. So I can only manage the right ones. And if I add more front-end recommenders, all they have to do is just decide on their client ID and group ID, and they will connect and start consuming these updates on their own. So it's very easy for me to scale. And we've created here some sort of a local bypass, right? Because most of the data is still going through MySQL replication, because most of the data is either not critical to be refreshed very fast, and either is not creating such a high load on our system to keep it fresh all the time. But some of the stuff that are very critical, and we will see what are those or what's the impact of it, are going through that bypass and injected directly to the caches. So if you go back to our data pipe, this is how it used to be before. I've moved things a little bit. So we added that binlog service right here in the middle, and it is reading all transactions from MasterDB, filters it, and wraps them up in a protobuf protocol message, and that gets written to Kafka. And on a side note, I will say that we don't have one Kafka because these are different regions. We have in each region, we have its own cluster of Kafka, and we have a mirroring service that mirrors from the main Kafka that we have on the backend to the local Kafkas on each front-end data center. We have a very good lecture about it, and if you want to hear about it, I can send you a link to YouTube to that lecture. We had to write our own mirroring service because of the large volumes that go through Kafka, and the Confluent Mirror Maker actually hasn't been able to solve that issue. It wasn't able to withstand that load. So I've done the second part because, again, I already had integrations with Kafka anywhere that I wanted. We already had that infrastructure. And the last thing would be to inject that change to all the relevant caches. So what we did is on each front-end recommender, we added a new embedded Kafka consumer. Actually, there's more than one now, but it doesn't really matter for the sake of it. But that's a little bit unorthodox. right? Because usually Kafka consumers are used on near real-time applications. They're used for stream processing and so on. You hardly see a web service that has a Kafka consumer within it. And what we've noticed is that the overhead of having one of those on CPU and memory footprint are very, very low. Okay, so the service does not even, it doesn't take any resources from the service, or hardly whatsoever takes resources. And what it does is that it reads those messages and decides what to do with them. But in most cases, it will inject that to the cache directly, and it will skip the DB fetch. And as I said before, all data must have a timestamp, because I want to keep consistency as asked here. And the really cool part about it is that once I've connected that cache to these updates, I can actually increase or remove completely the cache TTL. So now I can just remove completely the DB fetches. And once I've done the initial bootstrap from the database and getting all that information, I can get only the changes through Kafka. And that is a massive improvement. And I'll show you on the graphs later how much it does improve. And just to prove that it's really easy on our system to integrate it, all you have to do is create a Spring Bean that will inherit that interface, declare what tables that you want to support, and handle that proto message. So, well, I mean, it wasn't a really simple solution, but it was a very straightforward one. So great success. Everything was very successful. And if you have any questions, that'll be a good time. I see we have a new question. You have a concept of a quorum where you can set number of nodes first. Data needs to be copied before replaying. More quorum, the better the consistencies. So I think that this quorum level, this quorum question is not relevant when you're talking about MySQL, because MySQL doesn't really work this way. You write the changes to the master DB, and they get replicated to the slave. And if the slave hasn't received it yet, then it hasn't received it yet. It doesn't have the notion of quorum. Cassandra has that notion of quorum, and we usually work on local quorum, but that's a completely different topic. So for the first part, why not using Debezium connector for MySQL? I actually don't know Debezium, but the connector that we are using is very, very simple. And it allows me to control anything that I wanted. We started this project about 2 or 3 years ago. So I actually honestly don't know, and it's interesting. I will take a look at it. How reliable are these embedded Kafka consumers? How often do they have lags or other consumption issues? So it's a very good question, because it really depends on the service. So if that service doesn't have enough resources to allow that Kafka consumer to work flawlessly, then you will have lags. But as you can see, or you will see, we're actually saving a lot of load by using these Kafka consumers on that service. So I've never encountered any lags or consumption issues that we have. This is very, very, very stable. Most of the issues are on the other side of the pipeline. Most of the issues that we've had. How you handle Kafka outages? Kafka can point of failure. Okay, so this is a very good question. What we have is we have a mechanism of a heartbeat that the services are adaptive, and you will see it in one of the graphs later, that once they haven't received any message from Kafka or any heartbeat from the binlog service that they've been expecting for a few minutes, then they can decrease that TTL of them, or actually add a TTL, and then go back to the old method of updating it through the database. And there are effects for it, and it affects us, and we can leave temporary for a few hours, I think maybe more, with that kind of issues, but this is not something that we want to have on a steady state. Did you evaluate something that Debezium is something very similar to you? You did okay, I did not evaluate Debezium because, again, as I said, the library that we are using is so lightweight that this whole process of that binlog service is taking a core and a half on Kubernetes, and I think 2 or 4 gigabytes of RAM. So this is very, very lightweight. I don't see at the moment any reason to change it. Another question, since you're injecting data to cache directly, what prevents you from putting all required data in memcache ready similar? Why have MySQL slaves at all? Are there any? Okay, so the amount of data that I have on these MySQLs is tens of terabytes. I don't have all the working set on my caches on a single machine. The caches are LRU caches, and I cannot hold all that information. This is just way too much. So it's even way too much for memcached, right? Because again, tens of terabytes will translate to a lot of machines. Do you have multiple master databases? No, we don't have multiple master databases. We are thinking about doing a project and separating some of the master databases into several masters, but this is, again, this is very complicated. MySQL is not the gold standard for doing multiple masters. Okay, how do you handle DB schema evaluation changes? So this is not a problem at all because, again, we are still living in a place where our production system has to be backward compatible all the time, because deploying 1,000 servers, 1,000 founder recommenders is very complicated. You cannot do it all at once. So any change that you do has to be backward compatible. And the protobuf messages are actually key values of what you're passing on. So if you are backward compatible, then there is no issue with DB schema changes. We do not allow schema changes that are not backward compatible. All right, so I think these are all the questions. So just to recap what we had here, we are streaming changes from MySQL master using the binlog reader that we have, and we send only the relevant changes to Kafka, anything that we want to track. We consume the change information in all services. These are not only front-end recommender services. Many of our back-end services are actually reading these changes, and we inject the data directly to cache, and therefore saving a lot of load. And then show me some graphs, right? We are all engineers here. We all want to see graphs because I don't want to say all these things and just wave my hands. I want to prove it to you. So the first thing that I want to show you is how fast it is. Now, this graph is actually talking about 2 to 3 seconds until the data gets updated in the cache itself. And just to emphasize how blazing fast this is, this time that I'm measuring is including the begin transaction time. So the time starts when a transaction begins. It has to go through the database, and the transaction needs to be logged on the binlog. My service, the binlog reader service, actually has to read it, filter it, translate it into protobuf messages, write it to the local Kafka in the backend data center. The mirror service mirrors it to 7 global data centers across the world. Some of them are in Los Angeles, some of them in Hong Kong. Okay, this is very far in terms of network. And then the embedded Kafka consumer in each of the 1,000 front-end recommender servers needs to read that message, deserialize it, and apply the changes to the cache. So 2-3 seconds is blazing fast in consideration of all of these, and it is blazing fast in comparison to the best case scenario that we had on caches, which was 2 minutes. So this is, again, orders of magnitude faster than what we were used to having changes. And I've promised load reduction, right? Because fast changes they're not enough to have this complicated system. So the number of data changes that we have is way, way smaller than the cache updates. So assume that you have a cache with 500,000 records in it, and we have a bunch of those. Not all the records are changing on the very short TTL that you have. If you have a TTL of 2 minutes, not all the 500,000 records will change in this 2-minute window. But again, in this 2-minute window, if you are working with all these records, you will still go ahead and try to fetch them and serialize the same data over and over and over again. And experiments that we've done and now are live in our production system have proven that we can reduce our response time by 20% with this feature. This is a game changer, okay? And to show you the effect of it, I want to show you I did an experiment a few days ago. I took one machine and I've disabled the push updates feature. And you've already seen this graph of the updates per second on our by key caches. And as you can see, the second that I turned that feature off, I had a spike of about 10%, give or take, of more updates. And when I turned it on, it returned to the normal state. But that might not seem very impressive. Well, 10%, you're saying it's not a lot. But if you look at the machine load that was generated extra on that time, you will see that I jumped from the area of about 35, 36 to, well, above 40, okay? Above 40 all the time. And a machine with 40 cores that has a load of above 40 is not doing its optimal work. Okay, it means that there are more cores or more threads waiting to get CPU time than CPU that you have. So this is a massive impact. And only by reducing this, I'm able to withstand 10, 20, 30% the load without the change. Okay, so this is a game changer for us, and this allowed us as Taboola to be able to withstand our growth in the past year without buying any new hardware. Okay, well, this and other improvements, but this was one of the key components. And just to show the amount of queries per second on our front-end DBs, as you can see, we had an episode where our binlog service was down for an hour. And as I said, we are adaptive. So if we know that the binlog service is down, they will return to the original TTL. As you can see, the amount of queries per second has spiked and at 1.5x and sometimes more. Okay, so the impact is massive on our MySQL front-end machines, and this allows us to be able to withstand greater loads and not buying new machines. Okay. So, well, any questions up so far? Okay, I don't see any more new questions. Cool. So to conclude everything that I've said, we were able to speed up our HTTP responses by using caching, and by using the new method, we were able to reduce the load on the services and on the DBs the load that is created by the caching. And this solution is very easy to scale to more caches or even more services, because again, you're using Kafka, and that's very easy to just add another consumer. And a thing that actually jumped from it is as a new ability to use the stream data. We haven't had that ability before, and there are services now that are using that form of stream data, not on production applications, on some of them on the backend stuff. All right, so thank you very much. And if you want, you can follow our Scale Engineering meetup group. The link is published below. And thank you all for coming. And if you have any more questions, you can write them now, or thank you.
Thank you, Barak. And thank you, Ariel. Thank you, everyone, for joining us. If you have another question, this is the time, even to Ariel or Barak. Okay, people just write for both of you. Thanks. So thanks. It was really great presentations. So I just want to remind as well is that the talks will be uploaded to Wix Engineering Tech Talks as well. And actually, we have another question to Barak. How much time did it take to stabilize this pipe? I will send you just a second.
Actually, the Q&A started working now. I don't know what happened. So, okay. How much time did it take to stabilize this pipeline, having it reliably and work enough? So I would say that from day one, it worked with an availability of about 99%. But once in a while, you would get a bug or an event that was catastrophic, that it blew your mind. So right now, I have absolute confidence in it, but it's like any other system. It's a work in progress. You can always make it better. But the initial one, it was really fast, really fast. The first, I think it took us about 3 or 4 weeks until the entire design was implemented in a very basic way. Yeah, but it worked from the beginning quite well. It wasn't built for scale at the beginning, like I said, but it was an improvement. Does the front end do any direct writes to the master DB? No. So the master DB actually is on the backend data center, and there are no front ends there. And it's even more than that, because the front end machines are using a read-only connection to the front end database. They don't need to write any write that needs to go through the backend, because a single machine does not have the proper context to write stuff. They need to be aggregated back on the backend, because again, there are thousands of those, and you cannot write anything if you don't have the context of everything that's going on.
Okay, I think that